Okay, so welcome back. We are trying to prove that the metric space CAB with the Supremum metric is a complete metric space. To do that, we need to take an arbitrary sequence of continuous functions which are in this metric space, which is Cauchy according to this metric, and show that it does in fact converge to some function L of x, which is also an element of CAB. Okay, so what so far we've done is we have shown that if the sequence of functions is a Cauchy sequence of functions in this metric space CAB d infinity, then it necessarily is going to have a pointwise limit. And we've so far called this pointwise limit function, we've called it L of x basically. So we have got this orange function, if you like, which is the pointwise limit. So where every point x in the interval AB is mapped onto its pointwise limit, the pointwise limit of this sequence of functions. Okay, what we know is that if this sequence of functions converges in this metric space CAB with the Supremum metric, i.e. if it converges uniformly, then it necessarily is going to converge to this pointwise limit. So if you've got any hope at all of it converging uniformly, then it is going to converge to Lx. So now what we want to do is prove, using the Cauchy criterion and the pointwise convergence criterion, that together they are going to give us that this sequence of functions does in fact converge uniformly to L of x. Okay, and then once we've got that this continuous sequence of continuous functions does converge uniformly to L of x, then we apply the theorem from the previous set of videos on uniform convergence and of a sequence of continuous functions, and say that okay, L of x has to therefore be a continuous function, and therefore we've got L of x, which is an element of this set of continuous functions on the interval AB, and we've got that this sequence of continuous functions in CAB are converging uniformly to it. Therefore, we have a limit within the metric space, and it is complete. Okay, right, so let's try and prove that this is the case. So let's try and prove that this sequence of functions, f1 of x, f2 of x, f3 of x, etc., that this does indeed converge to the limit function Lx, which at the moment all we know is a pointwise limit for all this sequence of functions. Okay, right. So what would it mean? What do we need to prove in order to show that this does indeed converge to Lx? Okay, so we need to show what it would mean is that for any epsilon greater than 0, there would exist some big N, which is an element of the natural numbers, such that if little n is greater than or equal to big N, then it means that the distance in this the Supremum metric space between the function f little n of x and this limit function Lx is going to be less than epsilon. So basically that's just the definition of a limit in arbitrary metric space. So basically there must exist a point f big N of x such that if you take any term of this sequence of functions f little n of x, which is beyond this term f big N of x, then the distance between that term and the limit sequence is going to be less than epsilon. Now let's just replace this distance function here with what it actually is. So it's the Supremum over x as an element of the interval AB of the modulus of fnx minus Lx. Okay, and we need to make that less than epsilon. So we know that what this implies is that if we draw a picture, it implies that if we have this limit function here, this pointwise limit, so let's have this function here, L of x, then if this sequence of functions is going to converge uniformly, what it means is that I have to be able to construct you an epsilon interval around this limit function like this, and I have to be able to find your point in this sequence, f big N of x, such that that term and all terms after it, so all functions after it, f little n of x, are contained within the epsilon ribbon around this function L of x. And we know basically that this implies that the modulus of fnx minus Lx is going to be less than epsilon for all x is an element of AB. So that's just the symbolic language for this picture here, that all that function f little n of x has to be within the epsilon ribbon around the function L of x. And that occurs because if the supremum of this entire set here is less than epsilon, then that means that every element of that set is going to be less than epsilon. Okay, so I have to somehow find you a point in this sequence of functions for which this is true. Now, what we know is that that this sequence of functions is Cauchy. So that means that if we use the Cauchy criterion now, so if we say, okay, use epsilon over 2 basically, and because this is a sequence of Cauchy functions, sorry you can't see it, this sequence is a Cauchy sequence of functions, then if I let this epsilon over, if I use epsilon over 2, then there exists some, what should I call it, some big P. Should we use big P again? Yes, we'll use big P. There exists a big P, which is, in fact no, I won't use that, I'll use something different. We say there exists a big M, which is an element of the natural numbers, such that if, I won't use little n, what can we use now? If little g and little h, I don't think we use them for anything else, no. If little g and little h are greater than or equal to big M, then it implies that the distance between f little g of x and f little h of x, it should be less than epsilon over 2. So basically, if I draw out the sequence again, this is f1 of x, f2 of x, etc., there must exist some point f big M of x such that if you take any two functions beyond that tail end of the sequence, within that tail end of the sequence, the distance in this Supremum metric between them is going to be less than epsilon over 2. So you can do that because you can do it for whatever number you like that is greater than 0. Epsilon is greater than 0 by assumption, so epsilon over 2 is going to be greater than 0. Okay, right, so I can find you this point basically. Right, so now, what does that mean? That means that, again, just filling in what the d infinity means, it means that the supremum over x is an element of the interval AB of the modulus of fg of x minus fh of x is going to be less than epsilon over 2, basically. And we know that that corresponds to basically saying that if we have one function here, which is fg of x, and we have another function f of h of x, then the fh of x is going to be within this epsilon over 2 ribbon around fg of x, basically, like that, like so. Okay, so we're going to use this criterion, basically, along with the fact that this sequence of functions converges pointwise to L of x to prove that it converges uniformly to L of x. Okay, right, so the way we're going to do it is we have our epsilon, which is greater than 0. What we need to prove is that there exists some big N such that if you go beyond that, all of the distances of the function f little n of x from this function L of x is going to be less than epsilon. That's what we need to prove. So the way we're going to do it is by using the triangle inequality, basically. What we know is that it converges. What we know is that this sequence of functions converges uniformly. Converges pointwise to L of x. So what that means is that pick any x. So pick. In fact, we'll say pick any k, which is an element of this interval AB. Then what we know is that I can find you there exists a P is an element of the natural numbers such that if little p is greater than or equal to big P, it implies that the distance of f little p evaluated at k minus lk is going to be less than, and we're going to use as our epsilon, we're going to again use epsilon over 2. So basically what I'm saying is, if I draw another picture, here is the interval AB. We have some function on here which is L of x, and what we know is that this sequence of functions converges pointwise to this function L of x. So basically what that means is that if you pick a k, which is an element of this interval, and you make an epsilon over 2 interval, and unfortunately I'm going to have to make epsilon over 2 rather big in the picture. So if you pick an epsilon over 2 interval, something like that, then I can find you a point in the sequence of functions big P, such that for that function f big P, and for all functions after it, they are within the epsilon interval, at least to that point k. It might not be true that they are within the epsilon over 2 interval for all k after that big P. You'll have to find different p's basically, so this big P is going to depend on which k value you pick. But basically, for whatever k you give me, I can find you some p which is going to be a big P, which is a function of k. So for instance, if we imagine this k here, then big pk could be equal to 1,000. You might have to go to the 1,000th term of the sequence basically. So you might have to go f1x, f2x. You might have to go all the way down to 1,000, let's say, but that's pk of x. For another point, let's say a over here, you might have to go to a different number. You might have to go. In this case, it's obvious that it's closer in this case, but you might have to go further. You might have to go to 1 million or something. So pk is dependent on k basically. The point is that what we want to show is that there is a point big N such that all of the points x, which is an element of this interval ab, are going to be within the interval epsilon, are going to be of their corresponding point that the limit function L maps them onto. Right, so the way we're going to do that is I'm going to let big N equal big M basically. So I need to find you some big N such that this is true, such that the uniform convergence criterion is true, and basically I'm going to use the big N that I got from this Cauchy criterion, where I was using epsilon over 2 as my little number basically. Okay, so my claim is that if I go to this point, big M, in this sequence of functions, then for all functions beyond that in this sequence of functions, they are within the epsilon ribbon around the function L of x, basically. Okay, so how can I prove that? Well, the way I would have to prove that is I'd have to take an arbitrary point, so let k be an element of the interval ab. Okay, so I take an arbitrary point within the interval ab, and I need to show that the modulus of little n, let's say, we'll say, okay, so f little n of evaluated at k minus L of k, I need to show that that's going to be less than epsilon, basically. So I need to do, the way I'm doing this is I'm saying, okay, let k be an arbitrary point within this interval ab. So if we do it for an arbitrary point, if we keep it nice and general, then the same argument is going to work for all points in the interval ab, and therefore we've proven it for all points in the interval ab, which is what we need to prove. Okay, so so you might ask me, what is little n? Well, little n is just any number that is greater than or equal to big N, and of course we've said big N is now going to equal m. So basically, if you give me an epsilon, so let epsilon be greater than 0, and you are challenging me to find you a point big N, which is an element of the natural numbers, such that if you go to that term of this sequence of functions or beyond it, then for all of the points x in the interval ab, then the distance between the value that the function f little n ascribes the point x and the value that the function L ascribes the point x is going to be less than epsilon. That's what I'm trying to do. What I then do, you've challenged me to do that, and now what I do is I say, okay, we are given that this sequence of functions is Cauchy. Plug in epsilon over 2 into the Cauchy criterion, you will get some big M, which is an element of the natural numbers, such that if you pick any two functions that are beyond that f big M of x in this tail end of the sequence and ask what is the distance between them, it's going to be less than epsilon over 2. My claim is use that big M as your use that big M basically as your big N basically. From this point on, I claim all of those sequences will be within this epsilon ribbon. All of those functions will be within those that epsilon ribbon of Lx. Okay, and this is how I'm going to prove it. I'm going to say, okay, pick an arbitrary point in the interval AB. What I need to show is that if little n is greater than or equal to this M, so if I pick a point, a function in this tail end of this sequence, then I need to prove that it's within this epsilon ribbon, and the way I'm going to do that is show that it's true for an arbitrary k within the interval AB. Okay, and the way you do it, quite simply, is you say, okay, there is for this point k, there is pointwise convergence. So for k, there exists a pk, which is an element of the natural numbers, such that if little p is greater than or equal to big P, it implies that the distance between f little pk, and lk is going to be less than epsilon over 2. So the pointwise convergence of this sequence of functions to the function L we are now using. So we're saying you pick a point k, which you have done. The sequence of functions evaluated at that point k is a convergent sequence, and it converges to lk. Therefore, if I take, there must exist some natural number such that if you look at this sequence, this pointwise sequence, f1 evaluated at k, f2 evaluated at k, if you go along to the point fpk evaluated at k and pick any point beyond there in the sequence, then it's within its distance from the point L, the value lk is less than epsilon over 2. Right, now all I need is one of these, so you might as well pick the first one. Pick fpk basically. And now what we're going to do, in order to prove this, is just use the triangle inequality. We're going to say that the distance between the function f little n evaluated at k minus lk is going to be less than or equal to the distance from the function f n little k to the function to the value that the function f little p ascribes k, plus the distance that the function f little p ascribes k to the value that the function L ascribes k. Okay, so intuitively we need a picture for what we're actually doing. We're applying the triangle inequality, but a picture always helps with the triangle inequality. So basically, what we are saying is we have this interval AB, and we have some limit. We have some limit. We have some. What we have is some limiting. Well, we have some. This is the function which is the pointwise limit function of this sequence of functions. We then also have some function f little n of k. F little n of x rather, such that that function is beyond this f big M of x in this sequence of functions. So basically, this is Cauchy. This is Cauchy. This is within an epsilon ribbon. Any other function f little m of x, which is also beyond that f big M of x, is going to be within an epsilon over 2 ribbon of f little n of x. So basically, then what we can do is we say, okay, we've taken some little point k, and now what we can do is we can say, okay, we know that this is the pointwise limit, so I can certainly find you some function f little p of x such that that's within epsilon over 2 of the value f of L of k here. Okay, right. So then what we're doing is we're saying that the distance from fnk to lk, which is this distance here, the pink distance, is going to be less than or equal to the distance from lx to this p, which is this one over here, plus the distance from, let me get another colour, the distance from fnk to fpk. And because, that's a good point actually, I've made a mistake. You need to make sure that this is beyond, that the choice that you chose here was beyond big N. So actually, I've made a mistake there. The way you need to choose a function in this tail end, basically, here. You need to choose an f little p of k, basically. You need to choose a little p. And the way you need to choose a little p is so that it is bigger than the maximum of pk and big N, basically, because you need it to be in the Cauchy part of the sequence, and you also need it to be bigger than pk. In fact, you could just let it equal the maximum of them. That becomes important because you need this distance to be less than epsilon over 2, and it's only going to be less than epsilon over 2 if little n and little p are both greater than big M, i.e. if they're both within this tail end of this sequence, basically. So we need little p, we need to choose little p such that it's greater than or equal to big N, and we also need to choose it so that it's bigger than pk, so just take the maximum of them, basically, and that will get you both of the properties you want, because you want this one to be less than epsilon over 2, and making it greater than pk, or equal to pk, is going to assure you that that one, this distance here, is less than epsilon over 2, and making it greater than or equal to big N is going to assure you that that one is less than epsilon over 2. So basically what you're going to get is that when you add them together, this thing over here, the distance between fnk and lk is going to be strictly less than epsilon, and that's what we needed to prove in order to prove that this sequence of functions converges uniformly to this limit function L. So basically what we've done is we've said, okay, if we're going to prove that this sequence of functions converges uniformly to this function L, then we need to prove that for an arbitrary k in the interval AB, I can find you a point in this sequence, big N, such that all of the terms of the sequence beyond there are within the epsilon ribbon around the function L. So basically what I've done is I've said, okay, we'll apply the Cauchy criterion, find a point in the sequence of functions where the distance between any two functions is going to be less than epsilon over 2 if you take those two functions within the tail end of that sequence, and use that big M as our big N. And basically what we then wanted to prove is that if you take any function f little n of x, which is in that tail end, i.e. little n is greater than or equal to big N, then it's going to be within the epsilon ribbon. So to prove that it's within the epsilon ribbon, all we need to prove is that if you take an arbitrary k within the interval AB, that the distance between the value that the function f little n ascribes the value k, and the value that the limiting function ascribes k, the value k, is going to be less than epsilon. And that's what we've done using the triangle inequality, basically. The way in which we did it was by finding this fp, and the way we constructed p was by taking the maximum of pk and n, which gives us both of the properties that we need. Okay, so that overall proves that this sequence of functions, this sequence of continuous functions, does indeed converge uniformly to this pointwise limit if this sequence of functions is Cauchy. So what we've proven is that it does have a pointwise limit, and in fact it converges uniformly to that pointwise limit if it's Cauchy. Now we use the theorem from the previous video in which we stated that any sequence of continuous functions which converges uniformly is going to converge to a continuous function, which tells us that this function L of x must be a continuous function, since this sequence of continuous functions is converging uniformly to it. So what we have found is a function L of x, which is a continuous function such that this Cauchy sequence of continuous functions is converging uniformly to it. Therefore, we have the condition that this Cauchy sequence does have a limit within the metric space CAB with the Supremum metric, and therefore that since the Cauchy sequence is arbitrary, the metric space CAB with the Supremum metric is a complete metric space.